Hi, welcome everyone to my talk. My name is Trevor Yao Hong Ying, and I'm supervised by Professor Thomas Perrin and Dr. Shivam Basin. And the title of my talk is Deep Learning-Based Side Channel Analysis, Exploiting Vulnerabilities and Explaining Neural Network Decision. Great. So an outline of my talk is as follows. We go through an introduction of what side channel analysis is, what deep neural networks are, followed by 3 different aspects of deep learning-based side channel analysis. So an introduction. So what is side channel analysis? An overview of side channel analysis is as follows. We have a cryptographic implementation where we use to encrypt a message with a secret key. The goal of the attacker is to recover this secret key. Instead of attacking the underlying mathematical algorithm itself, the attacker actually can obtain physical leakage, such as power consumption or electromagnetic wave, also known as traces. By analyzing these traces, the attacker is able to recover the secret key. One generic trace acquisition setup is as follows. We have an oscilloscope with a sensor attached to it. Then the sensor is probed onto the device, and the device will run the cryptographic primitive. As it is running, the oscilloscope will record the traces, while the computer will simultaneously record the public variable, which could be a plain text or a ciphertext. A type of side channel attack is known as the profiling attack, where there is 2 devices, profiling device and target device. In the profiling device, the attacker may know the key or could even manipulate the key. For the target device, the key is unknown to the attacker, and we want to recover this secret key. So then profiling attack actually works in 2 phases, the profiling phase and the attack phase. In the profiling phase, the attacker obtains labels and traces from the profiling device to train a model. This model could be a Gaussian template, which gives rise to a type of profiling attack known as the template attack. After training this model is employed into the attack phase. In the attack phase, the attacker obtains traces from the target device, also known as the attack trace, and give it to the model to obtain a set of prediction. And this prediction, together with a pre-computed hypothetical labels, are used to compute a metric known as either guessing entropy or success rate to recover the secret key. So in this work, we're only going to focus on guessing entropy, which we denote it as GE. So if the attack is successful, that is when your guessing entropy is equal to 0. Furthermore, we also define another metric known as NTGE to be the least number of attack traces required for the guessing entropy to be equal to 0. This NTGE metric allows us to compare two different attacks that are successful. So if the NTGE is smaller, the better attack, because you require lesser attack trace to mount the attack. So then since 2015, 2016, there's a rise of there's an introduction of deep neural networks into side channel analysis. And this gives us the deep learning-based side channel analysis, DLSCA. So what are deep neural networks then? They are actually layers of weights trained for various tasks, and common deep neural networks for inside channel analysis are like multi-layer perceptron, MLPs, and convolution neural network, CNNs. So in this diagram over here is actually a diagram of a convolution neural network with convolution layers followed by pooling layers. Then it ends off with a fully connected layers. For MLP, it's just simply this fully connected layers only. Then one apply the deep neural network as the model to be trained for the profiling attack. So why does it actually attract so much attention? That's because there are multiple 2 advantages of deep neural network. Number 1, classical side channel analysis actually requires more attack trace to actually recover the secret key. It has been shown that deep neural network requires significantly lesser amount of trace to attack. And in fact, there are cases where it requires only 1 attack trace to recover the secret key. Secondly, In classical side channel analysis, pre-processing are needed to remove any under hiding countermeasure, such as desynchronization, or to obtain relevant sample point known as point of interest before the attack can be mounted. And these pre-processing are very tedious and arduous in nature. On the other hand, deep neural network-based attack requires little to no pre-processing needed. So this has actually garnered a lot of attention since 2016, and there has been a notable rise in the number of published works over this whole decade. Currently, there are over like 250 papers being published in this topic. So in our work, we look at three different aspects of deep learning side channel analysis, namely number one, artificial trace generation, hyperparameters of deep neural network, and interpretability of and explainability of deep neural network, all in the context of side channel analysis. So for the first, artificial trace generation, instead of using deep neural network as a distinguisher to help us find the key, we ask, could we use deep neural network to generate new traces? Why this is so? That is because in practical setting, there might be a limitation on the number of traces that can be collected by the adversary. For example, a typical use of a credit card is around 50,000 K, and a attack needs to be done within these 50,000 traces. If not, it will not be a threat it will not be a threat. So this will affect the performance of side channel analysis, and therefore there is a need for more data and more trace, and we want to actually generate new synthetic and artificial traces. But manually creating this artificial trace can be quite complicated and tedious because it is difficult to capture the leakage information and its characteristic properly. Some of the work has been done to improve and increase the data, like the use of SMOTch, which is a data augmentation technique, or just simply manually adding jitters into the original trace. Subsequent works try to make this automatic through the use of deep neural network, which is namely the use of conditional generative adversarial network, CGAN. However, GANs are known to be very difficult to train due to their unstable, it's very unstable due to their adversarial objective function they try to optimize. So in our work, we look into another type of deep neural network known as the diffusion model. The diffusion model are much more stable in training due to its likelihood objective function. So in this work, we utilize this diffusion model to automatically generate artificial trace that can capture leakage information. So what is diffusion model? Also known as denoising diffusion probabilistic model, DDPM. The idea is that at the start, during training, we start with training data, then we keep adding noise at each of the time step. Then we train the neural network to tell us what is the noise at each of these time steps. During inference, the noise, we start with to generate new traces, we start with a random noise. Then we use the trained neural network to try to remove every noise at each of the time step to obtain new data. So we apply this diffusion model into traces. In our work, we propose framework for two different settings. The no mask setting, where we employ an autoencoder together with a diffusion model to generate artificial trace. So what we found out was that we observed that the artificial trace that was generated by the diffusion model can actually preserve the leakage characteristic from the original trace. Furthermore, we also have this framework for unknown mask setting, where we use diffusion model to generate new training data for the profiling attack. And what we found out was that using this artificial trace, it can actually improve the performance of classical profiling attack, template attack, especially when the underlying primitive is protected by hiding countermeasure, which is desynchronization. And we see that the NTG actually dropped almost by half over here. This shows the effectiveness of using these artificial traces. Next, we look into the second aspect of DLSCA, the hyperparameters of deep neural networks. So we go back to using deep neural network as the distinguisher for this profiling attack. And it has been shown previously that DNN can indeed outperform classical side channel analysis, even in the presence of countermeasure. However, this actually introduces a large number of hyperparameters to be tuned compared to other machine learning techniques or classical side channel analysis. For example, the number of layers, the kernel size, the type of activation function, or the type of loss function, etc., etc. Previous work have actually pointed out that the performance of DNN is actually greatly influenced by their hyperparameters. This pushes for the need for methodology to find good hyperparameters in the domain of side channel analysis. So in our first work, we look into one particular hyperparameters, which is the loss function. We investigate the effectiveness of two deep feature loss functions, soft NN and center loss. So what is loss function? Loss function is just the objective that is being optimized when training the neural network. So this loss function will guide the neural network to how to update the weights. Then for deep features, it's just simply the intermediate layers of the output of each intermediate layers of the DNN. So common loss function in side channel analysis, like categorical cross entropy and custom-made loss function known as focal loss ratio. This loss function, they only consider the output of the deep neural network into their computation only. But for deep feature loss function, they consider also the deep features in the neural network into their computation. And in fact, for this common loss function, baseline loss function, they only consider the interclass distance. So what I mean by that is that suppose I have all the data points with just label dog and all the data points with all the label cats. What this loss function tries to do is just to separate them apart as much as possible. Well, deep feature loss function, they also consider the intra-class distance. So this means that instead of just doing this, they consider all the data points with labeled dogs, they try to minimize and make them as close as possible. Doing this will enhance the discriminative power of the neural network. And we hope that through this can improve the performance in DLSCA. So in our work, we show that indeed employing deep feature loss function can improve the performance of DLSCA attack. Next, we look into the hyperparameter process, where we use a type of hyperparameter tuning process called BOHB. So some of the works that has been done to try to tune these hyperparameters, at the start in CHES 2020, some works has provided some guidelines to offer more precise methodology that helps us generate smaller and well-performing DNN manually. Subsequent works try to automate this process because manually tuning these hyperparameters are very tedious and it can take up to months or days. So some automatic hyperparameters uses different techniques like Bayesian optimization, reinforcement learning, and evolutionary algorithm. However, most of these techniques are slow and could run for days, except for Bayesian optimization. So for our work, we try to improve on this framework. So some of the motivation is that due to the large number of IT products being evaluated, in evaluation that evaluating this product become very time sensitive. So resources such as time are actually valuable assets to determine the device security. So naturally, the evaluator want to set a budget for any of the resource, like time, to quantify the security of the primitive tested. So then the question is, are there actually automated tools available that can produce comparable results while allocating resource much more efficiently? So we apply this hyperparameter tuning process called the Bayesian optimization hyperband. So this BOHB is actually a multi-fidelity optimization method which allows speed up in the optimization process by allocating more resources to the promising ones and stopping the evaluation of poorly performing ones early. So in BOHP, they also introduced this parameter called the budget. So what would the budget be? Since we know that evaluation lab looks into the time taken, like manpower or the server hours, so we want to look into the amount of time taken or the number of epochs used to train a neural network. For those who do not understand what epoch means, it just means how many times you look through the whole data set to update the weights. Then since the amount of time taken and the number of epochs are equivalent, we simply just use the number of epochs as the budget for BOHB. And then we look into the objective function. So for Bayesian optimization, they require an objective function to guide the process of finding a good hyperparameter. So previous work has tried to look into these two loss function, validation loss and LM, and they found out that LM, this metric LM is actually the best objective function. But in our work, we propose a new objective function known as GE plus NTGE. And we consider the attack phase into the objective directly. Oh, give me a moment. Oh, it's not. Okay. On. And yeah. So this objective function actually consider the attack phase into the objective directly. And when in our work, we show that using our proposed objective function, we can obtain best result in 8 out of 14 of the scenario, which is majority of the case, and 3 out of 14 scenario for the previous two objective function. This shows the effectiveness of our objective function in finding good hyperparameters for DLSCA attack. Then next, we also show that using BOHB is able to recover the secret key for all the dataset tested. In fact, this is much more important for the evaluation lab, where it's more important to break the dataset than just getting the best result. So what I mean by that is, for example, I have 1,000 different dataset and primitive to be tested. It's more important for an evaluation lab to break all these 1,000 dataset than to just break one of them and did not break every other one. But this one, it actually obtained the best results. So it's better for the evaluation lab to obtain a tool that can help them find better result for all the dataset tested. Then furthermore, we also show that BOHB can actually attain best result for this CTF 2018 Hemingway leakage model compared to prior work, and it's the first to actually obtain less than 100 NTGE best. We also are the first to actually manage to recover the secret key for this CTF 2018 identity leakage model. This actually shows the effectiveness of BOHB in finding good hyperparameters in DLSCA. So then we look into the aspect of interpretability and explainability of deep neural network. So we have already seen that deep neural network can enhance the performance of key recovery. But deep neural network are still seen as a black box tool. The weights of the deep neural network are not human interpretable with respect to the underlying task. So we are unable to tell which area of the trace that the neural network are using to recover the secret key, and we do not know what the underlying leakage is actually exploiting. However, the evaluator still wants to help the developer localize and understand where the vulnerability actually comes from in order to remove or at least reduce them. So then the big question is, what did deep neural network learn when it successfully recovered the secret key? So in our first work, we use a neural network that is easy to interpret. Namely, we employ a transparent model that actually provides set equation to facilitate our understanding of neural network and pinpoint the point of interest used by this deep neural network. So, namely, we use this architecture called truth table deep convolution neural network TTD-CNN, which was proposed by one of our colleagues, Adrian Baramira. So the idea is just simply to binarize the input and the output, and then you can actually enumerate all the possible input to create a truth table. Then these weights are actually equivalent to this truth table. It's actually 1-to-1. So then we convert this truth table into set equation for interpretation, namely the disjunctive normal form, DNF. So what is DNF? Simply suppose I have x0, x1, or the xn is actually what we call a literal. Then the AND gate of all these literal give us a disjuncts. Then the conjunction of these disjuncts, which is the OR gate of all these disjuncts, give us the DNF. So an example of DNF is over here. X0, this one over here. So what we found after converting is that most of these disjuncts are actually unnecessary for key recovery. So we want to know what are these important disjuncts and literals in getting back the key. So we actually propose heuristic to analyze this set equation, and three types of them. Firstly, sifting disjunct based on their size. So size meaning the number of literals. So here there's a disjunct of size 4 because there's only 4 literals. Then we separate the disjunct based on their what we define as combination of literals, COL. So for example, a COL x1, x3, x5, x6 is just any disjunct with these 4 literals. No more, no less. Then we look into trimming the disjunct based on their literal. So what I mean is suppose I want to trim this x3, I simply just remove x3 from the disjuncts, regardless whether it has a NOT gate or not. So our goal was trying to find the most miniature set of rules that the neural network needs for key recovery. At the start, we actually try to train a neural network on based on TTD-CNN on the simulated trace. And what we found out was that this neural network actually overfit very fast due to it being a perfect world. So after some manual hyperparameter tuning, we actually managed to find this architecture called TTSCA small, and we convert this green color part into the truth table for interpretation. But in order for us to understand what the neural network is learning, we need to first understand the underlying countermeasure, namely masking. So masking, what it does is it actually split the secret information into different shares. And you can think of it just like thinking you split the key into many jigsaw puzzles and spread it out across the trace. Then the attacker or the adversary, in order to recover the secret key, need to take back all these jigsaw puzzles and then fix them back in order to recover this secret key. So formally, this is just we have a D+1 leakage point, L1 to LD+1, where D is what we call the masking order. It's just simply how many times we want to split this secret share into. Then we have a secret variable Z, and Z is just a function of G of this L1 to LD+1. And a common function of G is just the Boolean XOR of this leakage point. So we call this masking the Boolean masking. Then the simulated trace that we use to train is just simply this visualization here, where we have the leakage point at L and M1. Then XORing this L and M1 will give us the secret variable Z. So using TTSA small, we can actually observe what the neural network actually is seeing through the convolution operation. So we see at first time step is the orange box, then the blue box, and then the green box. So we use this simulated trace and train the neural network and recover the secret key of TTSA small. Then we convert it into set equation for interpretation. So using our heuristic, we first do it via the size. Then we see that the size of all this part, the orange line, it actually decreases. So the size 2 is the smaller size with Gaussian entropy equal to 0. Of course, one can look into other sizes, but our goal was to find a miniature set of rules. So we just simply look at the size 2. Then we look into the COL, the combination of literals, and we found out there's only one COL, which is just x1, x6. So there's not much to do here. So we just go to the third step, trimming, where we just simply trace x1 and x6 individually. And what we found out was that if you trim x1 and x6 individually, both of them will actually increase their Gaussian entropy to be more than 0. So this means that both x1 and x6 are needed for key recovery. And what do this x1 and x6 actually corresponds to? x1 actually corresponds to M1, where x6 actually corresponds to L in the second time step. So then overall, we show that TT-SCA small can pinpoint the leakage point and use it to retrieve the secret key. We obtain similar result for masking order 0, 1, 2, and 3. This validates our idea that through this set equation, the network is actually able to pinpoint the leakage position of the trace. In our work, we actually further extend this to real traces by proposing another architecture called TT-SCA big. And we are able to locate windows of point of interest that corresponds to the underlying leakage that the network actually used. In the best case, we actually managed to find the underlying masking formula through the set equation. Now we have looked into a transparent model. So what about a generic deep neural network? You might ask, the evaluator might be much more interested in a CNN or MLP, especially when they manage to recover the secret key. And we also know that this DNN can actually combine the shares implicitly to actually recover the secret key. And we know that the trace actually contains relevant and redundant sample points or features. So then the question is, what are the relevant sample points or features that are used by the trained deep neural network to obtain the secret key? So in our last work, we developed an explainability technique for generic DNN to locate the relevant sample point of interest used by this network. So we want to highlight that we assume here that the deep neural network is already trained and is already able to recover the secret key successfully. So our job was to try to explain this deep neural network. So we come up with this algorithm called key guessing occlusion, KGO. So what do KGO actually does? It takes all the index from x0 to xn-1 into an array. Then we shuffle it. Then one sample point at a time. We take, let's say, x3 over here. Then I occlude the sample point x3 of the attack trace. So what I mean by occlude is just simply replace this value of x3 with a baseline value. This is what we call occlusion. So in this case, this baseline value is just 0. Then we input into a deep neural network and rerun the attack phase. Then we get the Gaussian entropy. If the Gaussian entropy is less than 1, this means that this x3 is not useful for the deep neural network right now to recover the secret key. So we simply just throw this x3 away and keep the value at x3 to be 0 throughout the algorithm. Then we take the next sample point, x0, and we occlude it again and rerun the attack phase and get the Gaussian entropy. Now, suppose if the Gaussian entropy is more than or equal to 1, this means that this x0 is important right now for the deep neural network to recover the secret key. So we keep this x0 and replace back the original value of the attack phase. Then we keep doing for each of the sample point, and we get a set of sample point in index ref. But what we found out was that this can be done again to remove more sample points. So we redo it, and until the point where every single sample point in this index ref, wherever you remove it, the Gaussian entropy will be more than or equal to 1. So we call every single sample point over here op-POI. So we look into the number of op-POI obtained from KGO, and we found out that the number of op-POI is relatively smaller compared to the total number of sample points. In some cases, the least number of sample points actually require to we actually obtain the least number of sample points required to retrieve the secret key. For example, CW, Whisperer, and AES-HD, they are both unprotected. In fact, we actually obtain one sample point each. So this shows that deep neural network can actually just use that one single point to recover the key. So then we look into trying to explore what is the leakage within this POI. So we use a classical technique called correlation power analysis, CPA, which actually used to measure the linear relationship between the sample point and the given leakage model. So what we found out was that the POI from KGO shows that it is in line with the CPA, because this CPA is managed to recover the secret key. So this means that deep neural network can actually find sample points that are in line with classical techniques CPA. However, there are also scenarios where deep neural network actually found sample points that the classical technique actually missed. So we use over here we use this leakage model, but we also tried different leakage model and still could not recover the secret key. This means that the deep neural network is actually learning a much more complex function than a linear relationship to exploit the underlying leakage. Furthermore, we look into using this KGO algorithm to act as a feature selection tool. Why? That's because the number of POI is actually much smaller than the total number of sample points, and deep neural network can actually recover the secret key. This means that it contains exploitable leakage. So we apply it on template attack, the classical profiling attack, and compare it with classical feature selection tools and other explainability techniques. And what we found was that using KGO, we are managed to recover, as a feature selection tool, we managed to recover all the key for all the data sets. Furthermore, it can actually obtain a better result than second order CPA for SCART fix. This shows that KGO is actually much more stable compared to other techniques. Overall, my main contribution is as follows throughout my whole work, is that firstly, we look into artificial trace generation, where we use diffusion model to generate artificial trace that capture leakage information. Then we look into hyperparameter of the deep neural network by first looking at one type of hyperparameter, the loss function, and investigate the effectiveness of two deep feature loss function, stop and end and center loss. Then we look into the hyperparameter tuning process by applying BOHP that efficiently allocate resources when searching for well-performing deep neural network automatically. Lastly, we look into the interpretability and explainability of deep neural network by first looking into a transparent model known as the use of TT-DCNN that provides set formula to facilitate our understanding of the neural network and pinpoint the relevant sample point used by this DNN. Lastly, we developed an explainability technique called KGO for generic deep neural network to locate what are the point of interest used by this network. Some of the future direction that one can look into is number one, interpretability and explainability of DLSA. Although right now we can roughly know where the trace is looking at, however, we do not still understand what are the leakage function it is exploiting. So that is still an open problem. Furthermore, our work actually only emphasizes on a block cipher called AES. There are many other ciphers and primitives like the lightweight cipher, SCON, or the PQC, post-quantum cryptography ciphers like dilithium or Kyber. It might not be so easy to actually tweak it, to actually apply whatever that we use here. Some work needs to be done. Then there's also the deep learning based non-profiling attack, where the attacker only has one device instead of two devices, just the target device itself. Then the question will be, could our hyperparameter tuning process actually be used in this non-profiling attack? Lastly, blind side channel analysis, where the attacker do not have the public variable like the plain text or ciphertext due to practical reason, but only have the traces. Could deep neural network actually use to improve this technique? Some initial work has already been done by us, but more work needs to be done in this aspect of side channel analysis. So these are the journals and conference paper in this talk and in my thesis. And these are some of the papers that have been done throughout my PhD journey. These are the references in this talk. And I want to thank my supervisor, Thomas and Shivam, for giving me the opportunity to embark in this PhD journey and guiding me through this PhD journey. And I want to thank Professor Stefan from Red Bull University for giving me the chance to go to Netherlands to enjoy to learn more about deep learning based side channel analysis. Then I want to thank my colleagues and my researcher for the wonderful discussion that we have, and my family and friends for guiding me through this time of this journey. I want to thank my wife Emily for being there with me throughout this whole PhD, even though it's quite difficult. So this comes to the end of my talk. Thank you.
So I mean, we didn't say that the DLSP is like a black box, but my question is, if someone doesn't know much about lifetime analysis or cryptography, how easy for them would be to like use some of your methods?
Actually,
black box just to attack the
you mean as the framework or the explainability?
So like, do you think if you can build like a tool from this that someone doesn't know about lifetime analysis? Can that use it as a black box and then
Yes, it should be quite easy because actually recently there's a paper that by also Stefan actually has a tutorial of how to do it. And yeah, actually you can just, as long as you set up the data set, it'll be quite easy to run the whole thing. Yeah, actually I have a GitHub that is using on PyTorch. As long as you install PyTorch, you can run it easily.
So you have a truth table, because your input, I'm wondering, okay, so I work with deep learning frameworks, but obviously not in this application. You are taking traces from, for example, an oscilloscope or some real world input. The real world input is real numbers, right?
Yeah.
So you're converting that to
binary.
Converting that to binary.
Yes. So this will actually affects the performance actually.
Okay.
Yeah. But because we are doing the interpretability, and actually, for example, we actually have like batch normalization before that.
Okay. So you're compacting the values into a tighter and tighter space, and then you are
actually for the TTSA bit, we actually use a convolution layer before the conversion of it.
Conversion. Okay.
Yeah.
So if you, for example, you might auto encode into an integer space.
Something like
it easier.
Yeah.
And then in that integer space, you convert to the binary.
Yeah, we just force it on. But this will definitely affects the improvement of the performance, which is also one of the limitations in using this TTDCNN architecture.
I think all this the work surrounding explainability and interpretability obviously has ramifications outside of this this work, right? So for example, if I want to learn how GANs operate using this procedure.
Yes.
Possible.
Yeah, I would say what is your underlying task then? Like, because interpretability and explainability all stems from what are you trying to interpret. So what is your task that you are trying to do? You cannot just simply just plug and place, right? You need some modification as to what this set equation actually means. Convert can do a set equation and plug and place, but what do the set equation means at this for your task? Then that will be the question.
So if I have a camera that's looking at a picture of a dog, and then I want to see the centers the centers of the neural network that are being lit up, but at the camera level, I need to specify a set equation that makes sense. Then I can interpret.
You need to understand what the literals are. So what is x0, x1? What does it mean? Yeah.
So you talk about the deep learning based analysis. When I know in the chess community, there are a lot of people who are kind of against it. Do you know that counterpoints, and what is your counterpoint to that?
Okay, so the problem is that we can just throw it in, and many a times, so I talked to people and from evaluation lab, and they were saying that although these techniques all work in this public data set, which are quite easy, but then when you go into the real world, sometimes it becomes very difficult due to noise, due to different settings. But the problem, the thing is, it is still a viable research and something we need to look into because it poses a threat and there is still a possibility that this DLSCA still can attack and recover the secret key. Yeah.
In our laptop and three questions. The first question is about the trace generation. You mentioned that you use the diffusion model, right?
Yes.
And you briefly discussed some limitations of the trace generation with GNN model.
With
GNN model. Yeah, you just give a brief mention that if you use the GAN model to generate the
GAN, yes.
There are some limitations, right?
Which is that they are much more unstable.
Yeah. So have you implement some experiments to compare your method with GAN based?
I have not, but the previous two papers, like this paper, they were always talking about the convergence of the whole thing. So and then the question is how do I actually truly compare, right? Like that's also another question, which I think, yeah, because here when I apply it, if I put it into the autoencoder or any dimension reduction, most of the time it will work, although I still need to do some tuning to it. But for GAN, both of these work, they were saying that the loss, they were always looking at the loss function to do it. Yeah. So of course, more work needs to be done to compare the two of them. Like which one is way better than the other. Yeah. In terms of the stability and all this. Yeah.
My second question is there any unique challenge in temporal parameter tuning for that kind of analysis compared to other traditional computer science?
Yes. So I think the number one is that is for traditional like vision, computer science, computer vision, they just look at the accuracy. So that itself is just like immediately just check a linear check, right? But for side chain analysis, we need to look at this metric instead, guessing entropy and success rate, which actually uses n log n due to the sorting algorithm. So it actually causes it to be much more slower than the traditional one. Then yeah, so I think this is one of the biggest thing. And because accuracy does not actually most of the time you have low accuracy, but you still can recover the secret key.
Okay.
Yeah.
Okay, my final question is about ELCs you mainly discuss the test. So is there any idea to develop corresponding defense mechanism over this test?
There are some previous work that actually tries to use adversarial attack. So they try to see how much they use some adversarial attack to try to make the adversarial the trace to be a bit much more at certain point. So then in the hardware side, they try to increase certain like add more delays and all this. That's one way. Then other ways would be to just increase the noise even further by using a lot more random jitters and all these things. Yeah. So I think that's currently the technique to be done right now, from what I have read. That's the
different algorithms for your action.
no, yeah, the synchronization. So most of our, sorry, where is it? So, for example, this is desynchronization. Although we artificially added, we use some desynchronization towards it and check whether we can actually recover the secret key. So do some of this data set we do, some of this attack we actually do apply it on countermeasures. Yeah. And actually all of them have masking also. So masking is also another one that will also affects the the performance of the DRS unit. Yeah. Thank you.
Well, things that move forward. First question is the topic on slide 44. You mentioned that finding important data from this reading and simulated data. You also find some theoretical explanation on how these data are important.
Explain
Theoretically justify that for different use cases you can determine the data without having to answer simulation.
Simulation, but actually this is actually from the deep neural network though. So from the deep network you convert into set equation. So theoretical, if you want it to just from somewhere and then get it is a bit difficult. I got think about it before, but I don't know how to reverse it from that point.
You later mentioned that this was also working with the SAT, right?
That
And the SAT formulation, you go to the next slide and then validate that
yes.
through the SAT equation from network, we were able to pinpoint leakage position of the traffic. So that means what you're observing here with the PhD small or big is also matching with what you thought like 100%.
Yes, but the way to get this set is through gradient descent. So it's an automated process of training the neural network. Then after we convert it into set equations to understand what the neural network actually learns. So I don't think there's any theory or theoretical framework to actually look into this here. Not that I'm aware.
The question whether I will have to collect the test of the general test of running to PhD and determine the literals at the point of interest for the simulation, or I can approach this whole problem theoretically from a side equation.
The second part, not possible here. It's quite difficult. The first part is where you use the deep network to help me find the set equation, then it's possible. But the second part to get a theoretical framework to give me a set equation to recover a secret key is still quite a far fetch for now. And plus right now, like TTSA is not fully interpretable because the first layer is actually convolution neural network, and TTSA small, the first layer is actually a batch normalization. Although all this is still an equation, but I don't think there's any theoretical ideas as to why and how to actually develop these things.
So do you have a point where you say it's not computationally feasible and I'm taking over the saving method?
Oh, not really, because in the end we want to get a distinguisher, right? So it's we just run and give to the DLSCA.
Okay. So let me try to put it down that you are approaching deep learning website analysis, the big problem, right? And then the traditional methods of website analysis involve a lot of statistical techniques, finding correlation and where you can find point of interest. So what's the most compelling reason that you see where I will give over to a neural network or deep learning? Sorry. What is the compelling reason? What's the point where you say, okay, the statistical techniques will stay here and I have to give over to deep learning?
Actually, to be honest, we also don't know whether deep learning can actually recover the secret key. So sometimes it didn't recover the secret key, it could be just hyperparameter training problem and all these things. So I think both theoretical and classical we still need to test to be able to be sure whether
yeah, whether the thing, is it safe or not. Yeah, because it's still quite unreliable because of what I just said, like in evaluation that sometimes we never know whether this PRC can actually attack the server.
So if you try to get more specific to the ciphers, do you see that there are for certain ciphers or block ciphers or print ciphers, it works more effectively when I apply deep learning?
I don't think so because the issue is that you never see the whole trace at one go. So you can actually see everything in one shot to recover the data. So for now, the only problem, only thing that I see is that the noise of it being being the limitation of the attack, and then also what is the leakage model. So the leakage model will actually affect the performance of the DRSC. So then then in the end the cipher will actually decide what is your label you should give to the PDL, and that will affect the. So I think in SCON it's not as simple as just giving the output of the SBOX. You need some manipulation of the SBOX in order to get the result.
Do you see that evolving as a standardized testing approach? Like if I'm doing the component evaluation or fixed evaluation, then is there a step that I have to take with deep learning, which kind of models do I pick up from going training and all the start doing that?
Currently, I think it's already part of the criteria, and I think it's CIA, they already have some guidelines towards this thing. But of course, right now is that there are too many metrics, too many techniques. We don't know which of the techniques should be used and which case it should be used. So this is still a more work need to be done, but it's quite tedious. That's the problem. Yeah.
I have a question to also relate with the explainability of the regular network. Are there some techniques that you could learn from the deep learning based section that could be applied to the statistical thing? Because neural network also the form of statistical.
Yeah, actually, a reviewer actually once said that the explainability technique for KGO can be applied to template attack, but I didn't really go and try how it actually affects. Yeah, because template attack it looks also, but it has some kind of explainability in terms of the mean and the variance. Yeah. Okay.
You have the slide for your publication, right? You put it in the slide. People conferences. Do you try submit to some AI conference?
Submit to AI conference. Not much. I think it's mostly AIHWS is the only one, I think. Yeah. Because most of the work is mainly on the hardware. Thank you for coming. See you.